This is a production of Cornell University.
So actually recent research includes collaborative work on pruning and modeling, and also on the development and testing of microsensors for water status plants. And I spoke with you about that in the seminar. An integrated view of physiology of apple water related. Thank you.
Thanks, Tim. It's a pleasure to be here today and just to talk to you about some of the work that I've done over the last 40 years or so before I retired, well, and after as well. So I thought it would be useful with a lot of studies over the years. You study different components of a system, and it's kind of helpful to then stand back and take a look at the whole system and see maybe how those components can interact. So I thought apple-water relations would be a complex of interactions that might be of interest. The apple, of course, you're all familiar with domestic apples in general, but they actually have the center of origin in the lower mountains in Kazakhstan, the Tian Shan mountains, and this is actually a picture of apple forests in Kazakhstan, where the primary trees are all apples. And so the commercial varieties came from there. It turns out that there seems to be a rather narrow gene pool, so that our commercial varieties are relatively close to the wild types. And there's been very little, if any, breeding for water relations. It's been primarily for yield and fruit quality and sustainable bearing, but not for water relations. So we're really thinking of the plant as a wild plant. And so the climate there, I've been there, and it's a little hard to get good data from this remote area, but it appears to be an area with some dry periods in the summer, but not exactly Mediterranean. So period where it seems to be a moderate climate with dry periods in the summer. And of course, the leaf size and shape suggests that it's relatively mesotypic type of climate. So that's where we think the physiology evolves. Now, one way of looking at water relations was suggested by Neil Turner to look at a kind of a format for looking at the water relations as a group. So the first one is drought avoidance or escape. A lot of times we think of ephemerals growing in the desert as a way of escaping, but if a plant is able to grow in very cool season conditions, then that's a way of avoiding the midsummer drought condition. I'll talk about that. Another one is if they do have to grow through the summer, you can try to maintain the water potential at a high level. So even though there is stress, you tolerate the drought by maintaining high water potentials in the plant. And that's usually through reduction of water loss, thick cuticles, stomatal behavior, reduction of radiation absorbed, and the reduction of leaf area, those sorts of things. And another aspect of maintaining the water is to maintain the water uptake. So either increase root density or depth, finding more water, and or increase root conductivity, hydraulic conductivity to get the water potential maintained at the top. And of course, if it has to tolerate a more severe drought, then there's a few mechanisms such as osmotic adjustment to maintain turgor, and we'll mention that. Increase in cell elasticity and size is something that really hasn't been looked at significantly with apples, so I won't really get into that part. So let's look at some of these ways of looking at them, and then we'll look at some of the implications for practical growing. Okay, the avoidance issue, the growth habit of apple, there tends to be two types of shoots, although they're not strictly separated. And that is that In a mature plant, we have these very short shoots that produce a rosette of leaves. That's called they're called the spurs. And there's preformed leaves within that bud. And it's also the place that where the flowers and fruit are born. And so these preformed leaves come out very quickly in the spring. And then there are some lateral shoots off of that that can develop more leaf area. Typically, it tends to produce a short shoot, and so you get a little rosette with another short shoot on top of it. And that makes that spur complex that you see on the right. These come out very quickly in the spring, and they can develop a very significant canopy. And so at the bottom here, you can see a cornfield in late May. I don't know if that's actually typical or they just planted it, but in late May, this was a field that ended up being corn. And then on the right, you can see the canopy of apples is really quite well developed. They begin growing fairly early, mid-April. So the conditions are quite cool. The average temperature around 12 and 4 Celsius. And by about 40 days, or roughly 30 days or so after bloom, or after bud break, they bloom. And by that time, you have something in the neighborhood of 20 to 30% of the leaf area that they're going to have, and maybe 40, maybe up to 50% of the light intersection. So they have a very rapid canopy development, and they are able to develop a lot of that canopy and productivity before we have significant drought stress development. You should mention also the leaf fall in the autumn depends on temperature, not on photo period. So when you have a very long growing season, like in New Zealand or in northern Italy, they may have leaf fall in around Christmas time. Not New Zealand, but they can have very long growing seasons, and the leaves will stay on. If the weather stays good, they can stay on for a long time. I'll show later they can be very productive as well. So the other type of shoot are the extension shoots, which are the ones that can grow out the long internodes, so the leaves are spaced out. These can grow basically all season long. It's an indeterminate shoot, although it will set a bud, but if the weather conditions are good, it will grow, continue to grow, or it may regrow if the weather gets less stressful. So this is a way that the plant develops a very quick canopy in the spring, and then if the weather conditions allow and it's good water status, it will continue to grow far into the season. Very often here, we will see them stop growing basically by mid to late July, but they can grow. Some cases I've seen in northern Italy, they were actually growing in November. So it gives that flexibility, but they can also stop very, very quickly, and they may not only grow just a few centimeters if you have a very dry early part of the season. So it's a flexible response in terms of reducing the potential leaf area, at least, not necessarily excising leaves. So one of the other things that they mentioned is reduction in water loss. They mentioned cuticle, and apples do have quite a thick cuticle, so that's effective. But the variable one, obviously, is stomatal behavior, and this is something that's fairly unique with apple. And that is, if you look at the photosynthesis versus the leaf conductance, and this is in field trees under our normal summer conditions, you don't see that type of hyperbolic curve that you might expect with the opening of the stomates in photosynthesis. We almost always find a very linear relationship between them. stomates seem to be very highly coupled to the photosynthesis. And so we get a linear relationship. And the other thing we see is that they don't open any more than the photosynthesis continues to rise. So in most cases, you'll see the stomatal conductance opens more and more, and the photosynthesis levels out. And so you'll see it will tail off on the right side. We don't see that with apples. They tend to open up and estimate the stomatal limitations around 20–30%. And they just don't open up excessively under normal field conditions. Now this data actually is, I hid it. This is the actual data from 3 different sets of measurements. The pink squares are the controls that are healthy, well watered, no problem. The green triangles are from trees that are water stressed. And the blue symbols are from branches that we girdle the branch to cause feedback inhibition and shut down the photosynthesis. And yet, they all fall in exactly the same regression. So we've learned that over the years that that in the field we see a very, very strong coupling between the photosynthesis and the stomatal behavior, which is fairly unusual. And we, in the field, almost never see very high stomatal conductances. Now, I'll show you conditions where that's not true. But I mention that in the field, what happens is that because it's basically linear, you tend to have a very relatively constant water use efficiency, assuming at any big pressure deficit, because you're opening up the stomates at the same rate as the photosynthesis is going up. So the water use efficiency across that range is really quite constant. Where in many cases, if the stomates open up too much and the photosynthesis doesn't increase, you'll see it will decline the IN. So apples have a very, very good water use efficiency. Now, just to refute everything I said, apples have an interesting characteristic, and that is that they, if you look at the response to BPD, you see 2 different types of responses. Under very low stress conditions, so in many cases potted trees or growing in very, very low stress conditions in England, things like that, you'll find that the stomatal conductance at very humid conditions, low BPD, can go up very high. The stomates can open up very wide. But in the field, we see the blue markers down below where they, it will drop off at the high BPD, but they really don't respond to that, low BPD and high humidity. So they don't open up nearly as much as they normally would. These data are actually from the same branch on the same tree, but 3 days apart. If there's stress, they will behave like the blue markers where they don't respond to humidity. After 3 days of very humid, overcast, drizzly conditions, then the black markers show that they can open up very widely under low stress. And then about 2–3 days later, under normal conditions again, they had gone back down. So it's not a set response. It's a very dynamic response. And so I have some thoughts on why that is, but I don't really have time to go into that. So the stomatal response to BPD is quite unusual. What we think, the way we're interpreting that is that basically the green line just shows that there's a limit due to the humidity on the opening of the stomates. Perhaps the peristomal transpiration is limiting the opening, the green line. But in the field, we have a second response, and that is a limitation imposed by the coupling of the stomates to the photosynthesis. So like I showed earlier, if we girdled the shoot and the photosynthesis dropped by 80%, the stomates close. So under those conditions, where you have low photosynthesis, and it could be due to like a very low crop load, you get accumulation of carbohydrates, the photosynthesis goes down, then you get almost no response at all. So in many cases, we may see varying responses, but we think there's two interacting limits to this model opening. This will come back later with some modeling. Now, another thing is the reduction of leaf area. Apples don't really, they don't really excise leaves. They don't drop the leaves like in most cases. What it does is it stops producing new leaves. And by stop producing new leaves and retain old leaves, there's some real advantages in that you're not constantly having to build new leaves. So the respiration rates of apple trees, we've used whole canopy balloons. And in the middle of summer, the respiration on a sunny day, if it fixed 100 grams of carbohydrates or CO2, at night it may only respire 5 to 8% of that. It's very, very low respiration value because they're not producing a lot of new tissue. But to make that work, those old leaves have to be able to be productive for many, many months. And that is another unusual thing with apple, is that this plot shows the spur leaves we mentioned earlier that come out at the beginning of the season. They came out and they were first measured at the end of April. This is in Washington State. And basically their photosynthesis rate didn't change until the middle of October. And if you go out at this time of year, even to these long shoots that have leaves produced about every 2 days, so they have different ages, they all will give the same photosynthesis rate conditions. So they have a very, very slow turnover. They can stay in almost complete dark for 2 weeks. Take off the shades and they'll still be green. After a couple hours of acclimation to light, they will have close to normal photosynthesis. So the leaves on the interior don't really fall off. So it's an interesting combination between the water relations and the carbohydrate energy aspects of the plant. Okay, in terms of the radiation absorbed in relationship to the leaf area, again, as I mentioned, the leaves, it doesn't drop leaves. One of the characteristics that it does do is that the exterior leaves that are exposed to highlight fold, and if they're exposed to highlight and additional drought stress, they fold even more. And I've seen some where the margins almost touch. They fold it up so much. What this does is it reduces the energy load on that individual leaf. But of course, those leaves are out in the full sun normally, so that they're really not short of energy. So they can still photosynthesize at pretty much their maximum rate. But what it does is it allows light to be penetrating into the canopy where the interior leaves are flatter. So the lower the light, the flatter the leaf gets. And of course, they're growing in low light, so any additional light that they can get is used very efficiently. So it does seem that it should be increasing the water use efficiency of the whole canopy, though not necessarily reducing the total light intersection. Apple tends to be the type. It's not so conservative because it retains those old leaves, keeps them functional, and so and it doesn't drop leaves. So it doesn't really reduce its water loss dramatically as the other plants with the shutdown and drop leaves. But it sort of toughs out the moderate droughts. So I know a report that said in really dry conditions, apples are considered very drought sensitive because they can't make it through 2 to 3 months of stress. Where other things like grape will be very, will just shut down, drop leaves, and will get through the drought. But in shorter droughts, they can stay more productive. And so that seems to be their niche. Okay, the other aspect that I mentioned was maintenance of water uptake by increased root conductivity or reducing the resistance of that root system. Well, apple root systems have a relatively high hydraulic resistance, but they are able to adjust that in the roots. This study from my first student, Fred Davies, where we had potted apple trees, 2 or 3-year-old trees that we kept in a very humid glass house, so very low evaporative demand conditions. And then we put half of them out in a gravel lot area where it was much hotter and drier. And after several weeks, then we put them. We noticed that when we took water potential readings of the leaves, and in those 2 conditions, they had the same value, even though they're under dramatically different conditions. So we brought them together and estimated the resistance of the top and the roots, and we found that the tops didn't really change their hydraulic resistance, but the root changed by about 60%. So when it was out in the dry conditions, the root resistance decreased, allowing a higher conductivity for the water and actually maintaining the water potential at the same value. And I think this is when I talk to colleagues in Israel and Ireland and all over, well-watered tree in the middle of summer for them, they all tend to give about the same water potentials, even though they're living in quite dramatically different evaporative environments. So this is a quite strong effect. Anatomically, visually, we could not see the difference between these root systems. It wasn't a matter of one growing a lot of young white roots. They look basically identical. So we don't know exactly the mechanism. In terms of another way of maintaining turgor is osmotic adjustment. And this is something that apples do quite strongly. We've found that we can go up to 2.5 megapascals or 25 bars of osmotic adjustment. In a dry season, it takes time. It's not a very quick thing. It takes about a week to get maybe 3 or something like that. So it's kind of a long response. But when we started looking at it, we found that if you look at the osmotic potential of the shoot, the mature leaves basically all have a quite low osmotic potential, but the shoot tips have a much higher, much less osmotic potential. And over the season, we found that the shoot tips did not change in their water potential. So this makes those extension shoots that are growing, those shoot tips don't osmotically adjust, so they respond directly to the change in the water potential with a drying condition. However, the mature leaves do osmotically adjust. And so this allows them to maintain turgor over the season. And so you can see the mature leaves are responding to the type of conditions where the grown shoot tips basically are not osmotically adjusting at all. So that gives support for the older leaves and keeps the turgor and the water status of the older leaves better so they can be productive, which of course depends on them being able to be productive on a long time. So it's kind of makes a coherent picture there. This is a study from England where they looked at trees, and they found that on the bottom, the osmotic, the solid lines are irrigated, and the dash were non-irrigated drought stress. And you can see the osmotic potentials were relatively high early, and then went down from about 15 or 16 down to about 35 in the extreme. So about a 20-bar adjustment there. Well, the water potential was gradually going down also. The difference then is the turgor, and you can see that basically over the season that the osmotic adjustment was able to maintain the turgor both for the non-irrigated ones that went up and down, but also for the stressed ones and able to maintain the turgor. So osmotic adjustment is I think a very useful tool for the plant that has this type of response to water. Now we mentioned the roots and their hydraulic conductivity, but apple roots, especially in the modern orchards, they're not growing on the seedlings and the big root systems. Our modern orchards are using dwarf stocks that keep the plants maybe 2 meters or sometimes less in height. And so they have root systems that you can see in this picture can actually extend quite a ways, but they're not intensive. So a lot of studies have been done that find that the root length density of apples varies from 0, but up to about 0.5 or so on an average. I've seen, or 0.15. I've seen some values up to about 0.3, where they've got some data from corn. There's other plants even higher that they can go up to 30 centimeters per cubic centimeter of soil. So the implications of this is one is that if you have one root growing of an apple and you have 100 roots of corn or 1,000 roots of grass growing in the same volume, the grass is going to win. And we see that if you have a grass between the row, you don't get a lot of apple roots growing in that grass. They tend to grow in the other areas. And so that has an implication for practical growing. And grapes are very similar. They will try to avoid the competition of grasses and cover crops. Now, because of the high hydraulic conductivity, there's a very strong relationship between leaf water potential on the left and the transpiration rate. So the intercept at 0 transpiration is basically the soil water potential that's imposed on the plant. So that can go up and down a few bars, but the strongest effect is the transpiration effect. So because of that, and on the right you can see there's quite a strong diurnal pattern in the water potential of the apple trees. And they'll go down to, this is older data from Landsberg, with about 16 to 20 bars, and those are well watered. That's not a problem for them because of their osmotic adjustment. So we have this very strong diurnal pattern. The other implication of the low root length density, and this was calculated by Landsberg and Jones from the Gardner model, is that as the soil dries out, the rhizosphere resistance will tend to go up much more rapidly with low root length density. And basically, if you look at the estimates for apple water use in the field, estimates are something like, we up at 80, maybe even 90% of the amount that grass uses. So 80% of ETO. And so you have the apple trees are using almost the same amount of water as the grass, but they're taking it up with maybe 1/100th or 1/500th as many roots. So you've got very few roots that have to take up a lot of water. And so in the middle of the day, when they have a very high transpiration rate, the calculations suggest that there should be a significant localized drying around the root system. And there's actually some information, some data from Spain where they put on 150% of ET, and they got increased growth, and they had less negative midday water potentials than if they just put on 100% of ET at night before. And the rhizosphere depended only on the hydraulic conductivity of the soil to replace that water. So we think because of that low root bank density that we're having a significant rhizosphere increase in resistance in the middle of the day. And so it makes some of these estimations for modeling more difficult when you have that other component being extremely variable, as well as the plant itself. Now, another mention was maintenance of water uptake by increased root density or depth. The results of this have been really variable. In some cases, there has been a little bit of increase, as this plot from Zhao shows that the pink dotted line are the checks, and the other two are different stress levels, similar response. Where they tend to have somewhat less roots in the very top layers, and then in the middle zone they had somewhat more roots, and then lower didn't seem to make much difference. So they didn't seem to push them deeper, but they did have some more in that middle zone. But other studies have found basically no real response. So that doesn't seem to be a major mechanism for apple. Okay, I talked about some of the practical implications, things like estimating water use for irrigation, and how pruning might affect those things. Also, how we actually go about measuring those. We did work with student Motan Lee on the physiology of summer pruning, and that is when, typically around the 1st of August or so, you go out. If you have a lot of canopy, the apple fruit, the red ones essentially, need direct sunlight to get a good red color. And so there may be too much shade, and so the growers will go in and cut out long shoots that have grown away, and they can cut out quite a bit of leaf area. We actually estimated, we followed some growers that were doing some rather severe summer pruning, and they actually removed between 40 and 50% of leaf area, and to get the fruit as well exposed as possible. And so we did take a look at that using our whole canopy gas exchange systems that we've used for several studies, and we found that the canopy transpiration was reduced by that summer pruning, pretty much in proportion to the amount of leaf area removed. Not a one-to-one, but a linear response. And then after we did the summer pruning, we looked at the stem water potentials. The first columns on the left were just before the summer pruning, nice sunny day, and the stem water potential. You see they're basically the same. And then later in the day after the summer pruning, we did it again and found about a three bar adjustment of reduction in the level of stress, with a slight difference. So you could see that there was a difference caused by that, and then about a week later, the difference was still there. So in some ways, this may give the opportunity to try to reduce somewhat the stress on the fruit. It's kind of a compromise, though. If you have a heavy crop, you don't want to take up too much leaf area, or you won't get good size. But if you have a lower crop that's not limited by the amount of leaf area synthesis you're producing, this may be an opportunity to gain a little bit of that size back. But it's usually not used for that purpose. But we have seen that can affect. Not sure what happened there. Again. All right. We, in many cases, wanted to understand how much water being used to guide irrigation for our growers. And in some ways, we found that it seemed like we were irrigating more than we needed. And so the real question is, how do you estimate the water use of apples in our particular climate? Because we're not in California or Washington where they developed the estimates. And of course, it's hard to estimate that from soil moisture because of the variable root distributions and the cover crops. So we wanted to try to understand how to do that. And of course, the general approach is to use a Penman-Monteith equation. And for agricultural crops, usually the approach is to have a reference plant, a reference grass, or alfalfa, something like that, and use a model, Penman-Monteith, for that reference. And then your crop has a fraction of that. So that's the crop coefficient, or KC, is a fraction of grass values. It works okay in places like California, and it works okay when we have days that are like California. But it doesn't seem to work very well in New York. And so basically, shockingly, grass is not a very good model of an apple tree. So we thought, well, we need to take a look at this a little bit more detailed. We found that we were over-irrigating in using that crop coefficient approach from arid zones. We found we were over-irrigating in cool years. And it turns out the ETO is very, very strongly independent of radiation. If you look at the ETO and plotted against radiation, it's 93% R squared, something like that. So it doesn't have a very strong response to temperature, humidity. I'll talk about why. But in cases where we would have very cool, humid conditions, but sunny, we would get a high ETO, but we'd get low water use by the plant. And so we realized that with tall, rough structures, that we needed to look into how are they actually responding to the environment. Also, there was some theoretical study that suggested that crop coefficients that are developed in arid zones may not work correctly in humid zones. So if you look at an orchard and with the grass in between, you can see that for the grass down below, there's a heavy boundary layer, especially in orchards and vineyards where you have a windbreak about every 3 meters or so. So what happens is that you have a boundary layer that basically, when the humidity comes out of the plant and the stomate's open, it basically traps that humidity. So if the stomate's open, the BPD goes down. So they basically cancel each other out. And that's why they're pretty much just dependent on the radiation. That's not the case with the apple tree, in that because of the rough structure, there's very, very good airflow around the leaves. So if any humidity comes out of a leaf, it's immediately mixed with the bulk air. So then the stomatal opening makes a difference, and the radiation makes it, is the energy, of course, and the inherent BPD in the bulk air makes a big difference. So the two systems are being controlled by a different combination of factors. So we wanted to actually go take a look, but we wanted to be able to measure it directly. We used sap flow gauges, but we didn't trust them to make all the estimations of wound factors. So our student Danilo Grigoni did a study with using sap flow gauges, but we installed them and then we calibrated them with the whole canopy gas exchange for several days, and then removed the gas exchange chambers and let after calibrating them, let them go. We recalibrated later in the season. So this way we could get a really direct measurement, accurate measurement, but without disturbing the canopy environment. So when we did that, we found this is the actual crop coefficient, or the fraction of ETO. During this time of the season, it should be something like constant 0.8. You can see that's really not true. There are some days up here that were hot and dry and nice, like California, and there were some days that were cool and humid but sunny. So the high ETO but low water use by the vines or by the trees. So in this case, we could see that we really couldn't use the crop coefficients from arid climates, and so we developed our own apple-specific Penman-Monteith equation. And so, of course, we had to change for the boundary layer and other factors, but we did use this unique stomatal conductance, where in terms of the conductance versus the evaporative demand, the BPD, it goes down with the very dry conditions, but it flattens out and in the more moderate humid conditions. So we could not make the measured data fit the model until we put that unusual conductance relationship in there, and then we did get a good relationship with the model. So this model then was put onto the website of the Northeast Climate Center with Art and Keith put it on, and it calculates water balance for the growers using the data from the New World Weather Stations as a so it's been put into use. Now I mentioned that water status strongly affects many factors. Obviously, it can reduce photosynthesis, but it also reduces shoot growth rate. And as we implied from the lack of adjustment of the shoot tips, the shoot growth rate is pretty much linearly reduced by stress. In this case, we use stem water potential as the best integrative measurement. And then also fruit growth rate. Fruit tends to have a little bit of adjustment, and then it drops off with more severe stress. So these have a very strong effect. Water stress has a strong effect on growth and the canopy and the fruit. So really, how do we deal with that variability that we talk about? Because there's a strong transpiration effect, as we've shown. The soil variation can cause some variation there, but the weather patterns have a big effect on the transpiration. So it means that there's temporal variation going on, very dynamic and depending on the weather. In our crazy weather, you can imagine how variable it is. Spatial, also, many orchards are not in the most uniform soil. Some are, but many maybe on hills, or you have in areas where you get spatial variation in soils. And then there's a lot of physiological stage of development, those sorts of things. So trying to model all that to estimate what the actual water stress is in the plant is something that's really very difficult, and it's obviously best to just measure it correctly. And so, since, as mentioned, the water status of the plant depends on so many of these factors, all these parameters and the treatments and the soil water availability and where the roots are and where the soil water is and what the soil water content versus water potential release curve looks like. So there's so many different things. Why not just measure it correctly? And so, of course, we have done that for many, many years using the Scholander pressure chamber, or we call it the pressure bomb. It's manual. It's accurate. You get good. We get good data, but it's very slow and very limited data because of the manual nature. There can be some significant operator error, and it can lead to operator pain. And as you can see, lumbar 4 or 5 can take a hit. So in this case, after doing this for 40 years, or about 30 at the time, I said, well, we've got to come up with something. We got to somehow get this pressure bomb thing into some type of sensor that we can stick inside the plant and get continuous reading. We can sit back, put our feet up at the Contacted Abe Stroop in chem engineering, who's working on physics of water and plants, and we thought, well, the conventional soil tensiometer has a very good basic physical principle, and so if we could just turn that big one into a little chip, that we could make a micro version of that and then be able to insert it into the trunk or use it in soil, and then be able to get minute by minute type of data of the water stats. So that was the approach. This is Abe and Vinay Pagai, that some of you may remember, was a grad student. He was the first one to work with us on that, a joint horticulture chem engineering student. And he was followed up after he left by Michael Santiago, who had really developed it further as a practical tool. And then CU Zhu, working with Abe, is doing a lot of the testing now in apple and also in corn. So we're interested in seeing how that works. So the sensor itself is a sandwich. It's there's a water reservoir in there, but tiny 8 nanoliters, I believe, in there. It's a pressure transducer to measure the change in pressure. And then there's an exchange surface that you can see on the right, which is a perovskite silicon with nanometer types of pores. And because of that, we have a very large range. A normal tensiometer is about 1 bar or less. Ours will go, we had one go over 300 bars of stress. But 100 is sort of our standard. So we got a huge range. And then the chip is mounted into a cylindrical probe. You can see there next to the dime with the chip on the side. And this shows a little bit easier in the top left. You can see the chip on the edge there. We drill a hole with a guide and a special end mill bit to give a flat hole at the bottom. This is a prototype of a way to hold it to the tree, but we've developed further and some nice ways of installing it. And so this is studies from a couple of years ago when we had a drought. And you can see that the sensors in the apple tree, that's before all the installation. We have to do a lot of installation over that. But on a variably cloudy day, you can see the red line is the radiation, and the trunk stem water potential is buffered a little bit by the response time of the sensor, but seems to be a lot by the tree itself. There's capacitance that probably buffers out those things. And so you can see the type of data that we gather. It does correlate well with the pressure bond, except occasionally we'll get a early morning, there'll be kind of a spike. If you do sap flow gauges, you'll see it's a spike due to rapid changes in temperature. So we have to we do have a temperature sensor on that. So we actually have that now. This is a study that CU has done with potted apple trees, and you can see the diurnal pattern in the blue line, and then the pressure bond values are the orange dots. So it really is looking like the dream's coming true. And we do to get this actually available to growers. No big. It's a microelectromechanical system, MEMS, which is not something that most instrument companies do. The people that do it aren't interested in these types of applications. So we set up a small startup, and Michael Santiago is taking the lead on that, even though it was invited. But we're making a lot of really good progress on getting that available. Probably the first sales will be next year on it. So we're getting pretty excited about it actually being available. And of course, I'd like to acknowledge a lot of the people, especially on the left, Terrence Robinson, a colleague for 30 some odd years now. Did a lot of work with irrigation work, and taken this work to the field. And technicians, graduate students, it's not room to put them all up there. And some of the different sources of funding. But I really have to make a pitch for hatch and basic state funds, because nobody wants to pay for water relations studies in this kind of climate. They even say, well, why are you studying water relations in this climate? I said, well, in California, when they irrigate, they never have drought, because the plants always get the water they need. Here, if we don't have rain, then we get drought stress. So we have a lot more drought stress than they do in places that irrigate all the time. So okay, so I think over the years it's actually been very interesting, but I think there's actually some useful things come out of this type of study, and I'd like to thank you for your attention.
This has been a production of Cornell University, on the web at cornell.edu.